Good morning. All right. My first presentation is on ergodic standard deviation. This is basically a summary of the within event and between event standard deviations in the 14 candidate ground motion models that the TI team is currently evaluating. So you have the 5 NGA West 1 models, 5 NGA West 2 models, and the 4 non-NGA models, Akar et al., Bindi et al., Grazer and Kalkan and Zhao. So a lot of what I'm going to summarize has been discussed in the last couple of days, so this will be rather brief. We're starting with Abrahamson and Silva 2008. Okay, all my symbols are missing, but okay, I'll just talk about it. Do you have a pointer? Okay, so basically,
the pointer on the top.
Okay, this one? Okay, thank you. All right, so we have here Abrahamson and Silva 2008. They used the mixed effects approach to separate their within event and between event standard deviations. Both standard deviations are a function of period, magnitude, and they have included the soil nonlinearity effects, and this would be the parameters for that are VS30 and the median PGA rock. Their standard deviation, their within event standard deviation distinguished between measured and estimated VS30. Bohr and Atkinson 2008 used two-stage regression to estimate their standard deviations. Both of their standard deviation, the within event and between events, were function of period only. Their tau, or between event standard deviation, distinguished between specified versus unspecified style of faulting. Campbell and Bozornia 2008 used mixed effects algorithm. Their between event standard deviation is only function of period. The within event standard deviation is a function of, includes soil nonlinearity. I think it has magnitude as well, right? You didn't? Okay. Okay, I'm getting confused. Chu and Young's 2008 used mixed effects algorithm. Their tau, or between event standard deviation, changes with magnitude and spectral period. The within event standard deviation phi changes with magnitude, spectral period. It also distinguishes between aftershock and main shock, as well as inferred versus measured VS30. And they included the effects of soil nonlinearity on both phi and tau. Idris 2008 used one-stage regression algorithm, and they only provided total standard deviation, so they didn't estimate the between event and the within event standard deviations. All these models obviously use NGA West 1 data. They are applicable for a range of periods from 0.01 to 10 seconds, including PGA and PGV. Magnitude 5 to about 8.5, distance up to around 200 kilometers. VS30 from around 180 to 1500 meters per second. Now we're into the NGA West 2 models. The Abrahamson et al. Again used mixed effects algorithm. They are now having their within event and between event standard deviations function of spectral period, magnitude, and including the effects of soil nonlinearity. Their within event standard deviation distinguishes between measured versus estimated VS30. One new feature is that they have their within event standard deviation for Japan only, and then they have it for the rest of the data. Bohr et al. They used now mixed effects algorithm to estimate their within event and between event standard deviations. Their tau is a function of magnitude and spectral period, and their phi now is function of magnitude, distance, and VS30. Campbell and Bozornia used again mixed effects algorithm. Both of their phi and tau are function of period, magnitude, and include the effects of soil nonlinearity. Chu and Young's used mixed effects algorithm. Their within event and between event standard deviations are similar to the 2008 ones in the sense that they are a function of spectral period, magnitude, and they include soil nonlinearity. Idris' model again used the one-stage regression, so he only provided the total standard deviation. One feature here with these new NGA models is they are applicable for a range of magnitude from 3 to 8.5. They apply up to distances of 300 to 400 kilometers with the exception of Idris, and a range of VS30 of about 180 to 1500 meters per second. Now for the non-NGA models, we have the Akar et al. Model. They used mixed effects algorithm to estimate their between event and their within event standard deviations, and they are both a function of of spectral period. They're actually a constant for each period. Their within event standard deviation is relatively large, and we'll see that in the coming plots, and it's probably due to their small magnitude data. The Bindi et al. Model used mixed effects algorithm to estimate their phi and their tau, which are a function of spectral period only, and again their within event standard deviation phi is relatively large. The Grazer and Kalkan, we learned yesterday that they used the mixed effects algorithm. For now, we only have their total standard deviation, but they're going to provide us soon with their between event and within event standard deviations. The Zhao et al. Model used a mixed effects algorithm to estimate phi and tau, which are only function of spectral periods. Okay, so next I'm going to show comparison plots of phi, tau, and the total standard deviations for these four general scenarios: strike slip, magnitude 7, erupt 10 kilometers, dip of 90 degrees, strike slip, magnitude 8, erupt 200 kilometers, normal on the footwall, magnitude 6.5, erupt 15 kilometers, and reverse on the hanging wall, magnitude 6.5, and erupt 5 kilometers. And these plots are provided to me by Nick Greger. So this is the strike slip magnitude 7 scenario. On the left, you have the phi versus frequency. On the right, you have tau versus frequency. And then on the bottom is the total standard deviation. And some of the features, and again, this has been repeated over the last couple of days, is Bindi, Akar et al. And Zhao have relatively high phi compared to the rest of the models. For tau, we have Bindi again showing relatively high tau values. And this is here the total standard deviation, combining the two. Strike slip magnitude 8, distance 200 kilometers. We have here, again, Bindi, Zhao, and Akar et al. High. Now BSSA is coming up high, and I think this is function of because of the large distance. And you have tau here and the total standard deviation at the bottom. Normal on the footwall, magnitude 6.5. Again, same kind of observations for phi, tau, and the total sigma. Reverse, magnitude 6.5. This is very similar kind of standard deviations to the normal 6.5. And that's it.
Any questions for Linda on this, on their ergodic sigmas? Oh, hold on, wait for a microphone.
Good morning, this is Sinan Akar. Thank you, Linda, from METU. Only a comment, actually, or some sort of clarification. I have been communicating with my colleagues, the co-authors of ASP 13, and we really want to dig into this large magnitude, in particular phi. So within a month or so, will be providing you and as well as the scientific community the reason why we have large fee in terms of, most probably it is the poorly recorded, one of few poorly recorded earthquakes that inflates the fee. Thank you.
Thanks. Any other questions for Linda? This was the easy part on the segments, right? It's where you can go from here. No? Okay, let's move on to the next one.